those of you who did manage to get the recent updates, the notebook we're going to start with is in the policy gradient in the reinforced PyTorch section. And this one, as I've already mentioned, requires you to install OpenAI Gym, which can be done with this command. You ain't going to see it, but it's very simple. Pip install Gym. If you're running on a remote server, this is important. Only if you're running on a remote server via SSH or something, you should run this code. Otherwise, don't run it. It's probably not going to do anything, but on Windows, it's going to mess up with your installation a little bit. So what we're going to solve right now is this simple problem called cart poll. So this is a task where you are to teach this simple robot to move left or right in order to balance this pole on top of it. It's a very simple two-dimensional, so to say, reinforcement learning problem. But if your algorithm can't figure out how to learn this, it's going to have a hard time learning Atari and other more complicated stuff. So just to make sure your OpenAI Gym installation works correctly, you should see this picture right here. And you also should see this window. Just Alt-Tab out of it. You won't be able to close it. You won't be able to do anything to it. And if you do somehow, it's going to have consequences like ruining your IPython kernel. So just Alt-Tab from it and pretend it's not there. OK, so while you're doing so, I think we're going to try to do something about technical issues. Нашел? Чего нет? Ага. Так, микрофон врубается. Это хорошо. Давай, можешь, у тебя ноутбука нет здесь. Можешь налить на флешку тетрадку? Да. И у тебя тоже есть флешка? Тогда, наверное, она пригодится ему, потому что он сейчас идет наливать на флешку. I'm sorry for the inconvenience. It seems that GitHub, okay, it seems that a lot of you have some issues with installation due to poor internet connection. But if you do manage to see this folder, you should be fine. If you manage to find this reinforced PyTorch, you're more than fine. In fact, better than a median person in this room. And if you can see this guy, you're probably already on the edge of what we're currently doing. So we're going to implement an agent in PyTorch, which takes as an input the observation in this environment. And as action, it tries to predict whether to go left or right. Does this one work? Wonderful. Awesome. OK, so we're going to build an agent which takes an observation from this game, which looks roughly like this. Let me show. These are 4 numbers corresponding to a position of the card, the angle at which this pole currently is, and both velocity and angular velocity of this poor little robot we're going to torture with the reinforcement learning. And our agent has to take this observation and predict as an output probabilities of actions. So it's basically more or less the same as your yet another classification problem, where you predict whether or not to go left or right, but this time you're going to train it a little differently. So another variable that you have to get yourself acquainted with, this and actions. In order to begin, you have to define an architecture in PyTorch. You can either use sequential or PyTorch model or anything, which takes 4-dimensional observation, like a linear layer with 4 inputs, and produces probabilities of 2 actions. And in fact, it's recommended that you not predict probabilities, but predict logits, or the linear layer without softmax yet. Because in PyTorch, there is a way to make a more numerically stable logarithm of probability via log softmax. We're going to need this later. So just a simple neural network.
Guys, does everybody have the notebook? We have internet, so if you can't download it with this Wi-Fi, just raise a hand, and we will help you, okay?
So you can connect to Arseny network, and probably it will work for you.
Is it password free?
Yeah.
Yes, it's password free.
I think that 10 devices will be okay, but
Okay, so since we apparently have a situation where half of the people are already far ahead of us and the other half is still downloading the notebook, let it be as follows. You can get through most of the seminar by simply reading what it asks of you and going through the tests as those ones. So if you're ahead of us, just go ahead and don't wait for everyone else. And if you're not, well, we'll just, if you have any issues with downloading even after the internet connection, we're going to try to do this here together. Yes, and we also established yet another flash drive with pre-installed seminar. Raise your hand if you need it. Again, if you have any technical issues with your, okay, with installing Gym or with anything else, please raise your hand. We're going to reach you eventually. Yeah, if you've received the reinforced PyTorch, okay, if you received this notebook from the flash drive, then what you need is you have to skip this line. Again, just skip it unless you're on a server, like this. And it's going to be much simpler from this moment on because it was built to work in remote setup where you connect via SSH. Okay, my fellow deep learners, how do you implement neural networks in PyTorch? And then what? So apparently we have a 4-dimensional vector as an input and binary classification problem in the output space. The question is, what kind of layers are you going to use? Yeah, simple linear layers. So no convolutions required because apparently there is nothing that looks like an image. Any ideas on the dimension of this guy? Yeah, so it's going to be basically a state space dimension which is 4 by something. Let's say something. 20, 128. I'm going to start averaging over the ensemble. You've just abused my behavior. Okay, so let me remind you that we are building a neural network that has to learn to go right if it falls to the right and go left if it falls to the left. Yeah, so it can even be linear, but okay, pick whichever number you prefer. I will personally try just 100 because, okay, 128 because Misha said so. And he was the closest one, and I'm waiting votes with inverse exponent of the distance. Yeah, so and let's make another linear layer, which is going to be 128 to number of actions. Doesn't this network look odd to you? Something wrong with the network? Yeah, so it's kind of linear. And a quick vote, what's the default activation function? Fun. Which one? Elu or Elu? Okay. So be it. You can try any activation. The only thing I highly recommend you to not use is the vanilla sigmoid, because the input is not normalized, so sigmoid will gonna have problems with activations. So be it. The simpler ReLU. And you don't really have to go any further than that, but if you are to build a super complicated neural network that can solve much harder problems, we ain't gonna stop you. And now the question is how you actually apply it to predicting actions given this input. So you have states here. First thing you have to do is you have to convert states into a torch tensor. How do you do that? Okay. Yeah, torch is too obvious. Then what? You can even say it's going to be a float 32 tensor. And then what? Okay, so you have to predict action probabilities. Okay, not probabilities, but logits, which are obtained by just calling your agent. Agent, could you please predict logits given what? Well, yeah, states. And how do you convert those linear activations into probabilities? Yes, it should be roughly like torch.softmax in the newer version. If you have an older version of PyTorch by any chance, like torch 0.3, it's going to be torch.nn.functional.softmax. But let's hope you have the new version. And it's probably gonna start complaining if you won't provide it with dimension, along which it normalizes. Which dimension do we normalize over? The batch dimension or the action dimension? Yeah. So it's that simple. And apparently it isn't, because we have returned a torch tensor. How do we convert it backward to NumPy? Yeah. Data. Or detach NumPy or anything. If you're running on GPU, you'll have to convert it to CPU manually as well. So now we have a neural network which can predict action probabilities. So let me just show you. Let's say we create a new state, resetting the game. It's going to be a single state. And then we're going to call predict probabilities given this state. And then we have two probabilities, basically probabilities of going left and going right. Do you trust the action, do you trust the probabilities generated by agent? Would you use them in if you had to actually apply it to some real robot? Yeah, it's a random initialization. To be exact, it's probably some kind of glorat uniform or glorat normal, but it's definitely not a trained agent's output. But we can use it to actually build a reinforcement learning algorithm. Now, I want you to remember what methods Sergei Bortunov mentioned in his previous lecture, and again, how they worked in general. All reinforcement learning algorithms, they actually learn by first trying things. It's basically throwing a lot of stuff onto the wall and seeing what sticks. Just picking the sequences of actions that actually led to some positive outcome and trying to increase their probability. And the method we're actually going to implement is the policy gradient, aka the vanilla policy gradient, aka reinforce, which, as all other reinforcement learning methods, it should start by actually playing the game, trying actions with the probabilities, and measuring rewards. So first thing, we have this neat loop here. Let's go through it together to see what it does. So you have states, actions, and rewards. You want to gather sequences of states, actions, and the rewards you've got for those. And you gather them by starting in some initial state. then asking agent to predict what action he would prefer in this state, basically your probabilities, then picking your action, and then sending those actions, sending this action back into the environment. So it's the normal kind of Markov decision process, which should look roughly like this. So there is an agent. Is it visible with this font? Nice. Which one? Yeah, A is an action, which is, yes, a code, either 0 or 1, encoding 0 for going left and 1 for going right. So you have a loop with agent that predicts probabilities of action given state. Then you sample action from those probabilities. Action. It goes to the environment. And this is the env step, basically. And then after the step is performed, environment kindly suggests you that it has changed its state, and you have to rethink what your action is going to be on the next turn. So we record everything, and then we start over, but this time S is the new S. So yet again, we observe the next state, pick an action, make an environment step with this action, and so it goes. And this loop actually goes for as long as environment allows for it, because it has this neat Boolean variable called done, and if it is true, then environment is considered, the game is considered finished. Now, this is a common interface for all gym environments, so after we've managed to get it to work on this simple one, we're gonna switch to a more complicated environment. If we have enough time, that is, otherwise you'll have to do this on your own. So we have two options on what we can do. Either we can take the action with highest probability, or we can sample action with proportion to probability. This instruction suggests you to sample proportionally with probabilities. Do you have any suggestions on why sampling is better than just taking the most likely action? Yeah, exactly. If we're going to sample the most likely action, we're going to get identical experience all the time, and the agent is never going to learn anything different from what it currently does. So we have to explore. And in this case, we have to explore by sampling. Anyone already figured out how to do this? Yeah, so it's basically a question about using NumPy documentation. By the way, guys, just a quick survey. Could you please, finally, it's the final time, the final time. Could you please raise your hand if you didn't know about the Shift-Tab shortcut in Jupyter? OK, in Jupyter, you can press Shift-Tab in any function and see its parameters. And this kind of speeds up your performance in Jupyter by a factor of 10. In this case, we have to give it an array of what to choose from. Just either say 2, like 1 or 0, or give it the actions. Our actions are 0 or 1. What else do we have to specify? Which is to say what? OK, yeah, it's too obvious. So after we did this, what happens is our agent can generate session. And each session is going to consist of a sequence of states, like this. First state, second state, and so on. They change, apparently. Actions. Apparently random. And rewards. OK, just one reward, basically. Not just one reward, a reward for each step. And at this point, agent only lasted less than 20 ticks. Actually, let me guess. Let me evaluate what's the actual amount of time it spent. Yeah, exactly 20 ticks before it fell. If we run this thing again, the number is going to be slightly different. But it doesn't change the general idea. Our agent sucks. We're going to need to train it to perform better. The first thing we have to do to actually begin training our agent is to evaluate its performance, is to kind of convert those kind of those simple rewards into something more something more evident about his general performance in this game. And there is a technique for that, which apparently wasn't covered on the lecture. Did you cover discounted rewards? No. OK, so there is a technique for that. Let me just quickly go through it. So there are rewards. But the problem is that the rewards in this game are always 1 until you fall. So you begin in like this balanced state. Then something happens. Then you fall. And you get rewards of +1 for every step you managed to do before you fell. So the first question is it true that we can consider an action to be good if it received a +1 reward? No. Why? Yeah. You might have, so for example, this action, it did give you +1 reward, the last one, so it's like state last action. You were given +1 reward, but it was the last thing you managed to do before the agent fell. And we are trying to punish our agent and kind of avoid doing such actions in future. So there's a framework for that, which is as follows. We have to maximize, we have to measure action performance not by what agent managed to get right now, but with what he managed to get from this state on, starting from this moment on and until the end of the game. So if your action led to you living long and prospering, no reference intended, then it's going to be beneficial. And if it gave you reward, but then you fell and got nothing else, then it's going to be less so. So the idea is as follows. So you have, with this game, again, what I'm drawing here is you have a state, you move to the next state with an action, and then next state with second action, and so on. We're going to compute for this particular state and for all other states a sum of all rewards starting from this reward and until the end of the game. In this particular case, it's equal to the number of steps, but it's going to be different in other games we're going to switch to. And another quirk right here is that we don't just add up all the rewards, we actually multiply them by coefficients. So the idea here is that you compute the thing called G. I'll write it in this large font so that everyone can see it. OK, it's too low probably, right? I'll write it. So we're going to compute a thing which is equal to your current reward plus your next reward multiplied by a discount factor, say 0.9. Plus the reward in 2 steps multiplied by discount factor, say 0.9 squared, 0.81, and so on and so forth until you reach the end of the game. So what you need to compute is basically G at the moment T equals reward plus this discount factor times reward at the next step. And so on, until you reach the terminal state. It's going to be RT. And it's going to be multiplied by gamma with which power? To which power? Yeah, so basically, however many steps you made here, you add up one more power of gamma for every step in the difference between t and this particular step. So it's going to be, again, gamma to the power of t capital minus t small. OK, so this particular formula is something you need to compute right here for all the rewards. So for the first, for the last moment, this thing is apparently equal just to the reward itself. This one is, for this moment, g is equal to 1 plus gamma times this one. For the third one, it's 1 plus gamma times this one plus gamma times this guy. And again, we are deliberately writing it explicitly. I know you could compute this as a sum of geometric series, but this rewards can be arbitrary values, not just ones. So your main task at this point is to implement a function which computes those cumulative rewards. And you're going to need them later in the distributional RL. The whole idea of Q-learning is based on those rewards. So the question to you to kind of ask aloud is, how do you want to compute those G's? Can you compute them in parallel? No, they are better suited for sequential computation, right? Which G would you prefer to compute first? Yeah, the last one. And then you can recursively go from the kind of last one to one before the last, and so on and so forth in a loop. Again, please implement it and get through those asserts. Here are some values. So if those are your rewards, then those are your Gs. The rest of us are doing this assignment. If you feel that you are much more competent and you're already aware of many RL methods much more efficient than this one, then for you we have this second part where you have to implement a recurrent neural network-based actor critique algorithm. Again, just go with the, just follow the instructions from there. But otherwise, we invite you to still stick to this one, because the second one builds on the first. So if you feel bored and want to feel overwhelmed, you can switch. Yeah, this is a terrible mistake of mine. This negative sign should actually be a plus. Thank you. Yeah, and in order to avoid any mental damage, please don't try to compute this thing in pure NumPy without loops. This may damage your brain. Yeah, it will be either quadratic, by multiplying by a lower triangular matrix with those gammas, or it's going to be with SciPy something, something, signal, something, something, some kind of convolution-like operation. We'll wait for a few more minutes and then go through it. Yeah, exactly. So you have to, given rewards, the rewards given here, you have to produce gammas, Gs, return an array of cumulative returns, cumulative rewards. And for the reference example, it should look like this. OK, so let's implement this stuff together so that we can finally get to learning part of the reinforcement learning. OK, so I'm going to create this array of Gs. At the initial point, they're going to be it's going to be an empty array, and the only thing we can compute from the offset, we can say that the last G is going to equal to what? It's basically a rewards at -1, which is the last reward, and then let's iteratively insert insert a previous G given the next one. So we're going to iterate from the last reward to the first. So excluding the rewards at index -1, reverse that. I deliberately write the maybe not the most efficient, but the simplest to kind of, I guess, to understand code. But in fact, what we the main kind of the meat, the math of this thing is to implement a recurrent expression to compute the previous G, given the next one. How do you compute the previous G? You take the next G, which is basically at our point, this is the next G. Okay, G next. And then you take the next G and do what? Yeah, you multiply it by the discount, which is gamma. And then, is it all? Yeah, and you add the reward. And you can now insert this to the beginning. Just saying, insert operation on a Pythonic list costs linear in the length of this list. So this is not a very efficient algorithm. But apparently, you could simply optimize it by computing the inverse sequence of Gs and then reversing it at the very end. Yeah, S for gamma to the power of t. So let's see what happens. The last G is just rewards. Then we get previous rewards plus gamma times rewards. And then we get, at one step before that, we get previous rewards. So let me just draw it. Last one, GT equals just RT. GT minus 1 equals RT minus 1 plus gamma times reward T, which is the same as GT. And then what's going to happen is we're going to go through the brackets. So there's going to be a GT minus 2 equal to RT minus 2 plus gamma times this expression. Gamma times RT minus 1 plus gamma times RT. So if you open the brackets, this expression is going to look exactly like this one. So we're going to have gamma times reward at the next step plus gamma times reward at the final step. So this is a simple recurrent way to compute those guys for all time steps. And hopefully it works. Yes, it works. So I'll leave this code for you to observe in a minute, but before I do so, let's actually get to learning. So we managed to implement all the preliminaries. We built an agent which can predict actions, action probabilities to be exact. And then we made this action, this agent play sessions. We've implemented this generate session method right here. So it can sample as many trajectories, as many games as you want for your learning algorithm. And we've also managed to estimate the performance of his every action with these cumulative rewards. Now we're going to try to maximize those cumulative rewards by iterating over agent's policy. And we're going to do so with this reinforce. So again, OK, so let me clarify a little bit. What we actually want to maximize is the expectation of those Gs. So basically, it's not exactly the function here, but this function is what we're going to implement for PyTorch. So our objective, our kind of mathematical objective, is to maximize the expected returns. But in order to do so, we're going to follow the policy gradient. One thing Sergey should have mentioned in his previous lecture was that if you want to compute a derivative of the expectation with respect to the policy, the probabilities within this expectation, then you can do so with a log derivative trick. Basically, the mathematical truth here would be to say that derivative of expected returns equals derivative of logarithm of the probability times the cumulative returns. And this is exactly the thing we're going to write, this function, so that when PyTorch differentiates, when PyTorch computes the derivatives with backprop, you're going to get exactly the policy gradient. Just to make sure, so how deep did Sergey go into policy gradient? Did you cover log derivative trick to begin with? Yeah, nice. And as you did you cover baselines for? Yesterday? Not for instance, like in general. Ah. I see. All right, so we're going to implement this loss function, basically this guy, in order to optimize it with Torch Optimizer. And we're going to do so by predicting logits. Here you have to just apply your agent. Then computing probabilities and log probabilities. And implementing this thingy, this nabla logarithm, okay, this logarithm of policy times discounted rewards, which are given to you here. So those get cumulative reward get cumulative rewards function you've just written is already used here to measure the performance of agents' actions at each moment of time. But there's one more thing we have to do. In order for this algorithm to converge more predictably, more reproducibly, we also regularize it. We don't just maximize the expected reward, the expected cumulative returns, But we also maximize the entropy a little bit. There is an entropy regularizer. So what we do is we take agents' action probabilities, and then we compute the entropy of those probabilities, and then we kindly prompt our agent to, with everything else set to equal, to maximize the entropy. The question to you then is, what probability distribution over two actions has maximum entropy? Yeah, uniform distribution with 0.5 and 0.5 probability assigned to each possible action. And this is required to prevent agent from collapsing into a one-hot kind of probabilities, because reinforcement learning methods, as I've mentioned, as you have mentioned, they actually learn by exploring the environment. So you want your agent not to pick the same action all the time, but to explore, to pick different actions to see what the outcome is. So if your agent, by some accident, say the gradient exploded, and now it starts to predict the probability of going left 100% and going right 0%, then it's never going to learn that maybe in this situation going right was the right thing. So to prevent that, we regularize, we ask our agent to also maximize entropy, and therefore his distribution will be closer to uniform. It's like L2 regularization, but for reinforcement learning. Okay, so just to make sure, does anyone still require this thing to be present on the slide? Say if you're still fighting through it. Okay, raise your hand if you object to me going going further and not showing this thing here. 3, 2, 1. Okay, so as usual, we can just ask our agent, can he please compute actions given states? And then using those legits, you can compute probabilities, it's softmax, and log probabilities with log softmax. Okay, so there's been a few questions about what the heck are we doing and why are all those logarithms out there, and what the entropy is doing in this formula and so on. So let me recapitulate what should have probably been there on the lecture. So we want to maximize this. We want to argmax of this expression, which is your expected cumulative return, how well your agent performs, how efficient does he pick actions, plus some coefficient times the entropy. And we want to do so by maximizing over the policy, over agent's neural network, basically. So as for those two terms, the first term is simply the better you get, the higher reward you get, the better. And the second term is the one that actually slightly turns your agent in favor of not being too certain. So instead of 100% going right, he would converge to a situation where he goes right, say 90% of the time, and then 10% of the time he goes left. And this is required so that no matter how high or low his reward gets, he keeps trying alternative actions. In reinforcement learning, the exploration of all possible actions is key, because you only get to learn on the trajectories, on the games that your agent itself managed to produce. And if your agent never does something, it will never learn that this something might be good. It's like cavemen. They never learn to, until you actually see the wheel, until you build the wheel, until you until you somehow randomly stumbled into a way to move large loads over long distances with the wheel, you don't invent the wheel. You don't invent the wheel by just sitting below a tree and eating a banana. Any questions? It should get pretty high after a few steps. Maybe show me the code for the loss function. Yeah, guys, and another very popular question, which should be answered here, I guess. Can someone please tell me what's the formula for the entropy of the probability distribution? Yeah, negative, so it's minus sum of probability times log probability. Basically, it's a probability of action I, summed over all possible actions. In this case, it's 0 or 1. There are two key points that a lot of you might need to check in your implementation. First thing is negative. And second thing is sum, as in not average. So let's go through the implementation. You have logits predicted by your agent. What? G? These are cumulative returns. These are reward plus gamma times next reward and so on. OK, so how do you predict probabilities again? Yeah, you ask Torch to do softmax for you. Of what? Yeah. And as for the log probabilities, that's the reason we asked you to not introduce softmax inside the neural network, because Torch has a built-in log softmax. Yeah, thanks. Sorry, I've almost missed this one. OK, so as for log softmax, just to make sure we're on the same page, the log softmax is what you get if you simplify the expression for the logarithm of softmax. Basically, if you compute a logarithm of softmax, it's a logarithm of exponent divided by sum of exponents. And this logarithm of exponent should probably ring a bell. If we rewrite this logarithm of, first, we can rewrite this logarithm of one thing divided by the other into a difference of logarithms. So this is equal to logarithm of exponent to the power of, OK, some logit. It's not action, it's just some arbitrary a, minus logarithm of sum of exponents. And of this expression, there is one more simplification you can do. Yeah, logarithm of exponent of a is just a. And this is what log softmax does. The reason we actually use it is not just to save a few CPU loops. It's to make softmax formula harder to collapse into none. So if, for example, this thing is very small, then if you divide this thing by this one, you can get something which will be numerically rounded to 0. Like float 32 precision will be insufficient to cover how small it is, so it's 0. And logarithm of 0 is negative infinity, which yields you none after you average. So to circumvent this problem, we avoid the division at all, instead with subtract logarithms. OK, so you have log probabilities of actions here, and you have the cumulative returns. How do you compute the expression that we use as our objective? Something whose derivative will be derivative of expected g. Any ideas? Yeah. So you take log probabilities, but not all log probabilities, only for your actions. This is, again, super important because those are log probabilities for both going left and going right. And your agent can only be punished for what action he did. So you either encourage you either reinforce or negatively reinforce not all actions, but the action he picked. OK, it picked. Sorry, it's too personal. And you multiply it by your g. What? It shouldn't be negative as a value, but it should have a negative sign before it. This is not entropy yet. Entropy is this guy. Entropy is a sum of all possible, for all possible actions, of their probabilities times this log probabilities. How do you compute that? Yes, with a negative sign. Yeah, you torch sum of what? Yeah, you take probabilities not for actions, but for all actions. Not for chosen actions, but for all actions, times the log probabilities. And to be completely honest, this is a sum only over actions. And you have a tensor which has a size of batch size times action size. So you only should sum over the last dimension. Otherwise, you're going to sum over all examples in the batch. And over examples, you can instead compute a mean. This is not strictly necessary, but it can mess with the relative importance of maximizing reward versus maximizing the entropy. And now you do what you did in all the previous deep learning seminars. You optimize with PyTorch. There is a space for you to define optimizer. It could be RMS probe, Atom, Momentum, vanilla SGD, random search. Okay, anything you want. Just don't use LBFGS because it's not the same. It's not that good with stochastic gradient descent. And you step. Okay, you backward, then you step, then you zero grad. So the most popular optimizer that almost everyone uses if there are no arguments against it is Atom. So you can create optimizer by using torch. Was it Optim? Atom. And you ask your optimizer to minimize a loss function over parameters. What are the parameters? Who do you? Yeah, so you have an agent, which is a neural network, who has those parameters, and you simply ask Atom to minimize over those parameters. So you have your optimizer, and then what do you do? Yeah, first let's backprop. This syntax is so backward. Then, yeah, you perform the iteration of this Atom, and then, yeah, so then you have buffers for gradients after backward that you no longer need, so you zero them. You can also agent.zeroGrad that is going to do the same thing. Okay, so here it comes. We compute the derivative, okay, the formula for derivative of expected return right here. And we also regularize it with entropy. Let's see if it trains. Now, what you should see is you should see numbers that more or less grow over time and at least attempt to reach something like at least 50. Depending on your neural network architecture, you're going to see more or less stable and more or less fast growth. And as we can see right here, there is a surge almost to 300s. But then then the algorithm dropped. The reason for this is that this algorithm is not very stable by design. It trains on its own samples. And there may be, for example, such a situation where your agent, say, goes to the left for 10 sessions in a row, and by training on those sessions and on nothing else, it forgets how to perform if you went to the right. So since your neural network is trained on agent's own experience, any irregularities in agent's performance can cause such fallbacks. There are much more stable methods like trust region policy optimization or proximal policy optimization or others. But in general, you should see that reward grows from whatever initial value you had to something better. Its normal performance is to oscillate around 300 or 400, depending on your network architecture. And if you want to, at this point, a lot of you might be comparing this to what you have in Notebook and finding some difference. So please raise your hand if you have any issues. Yes, and if you're seeing numbers grow but never reach 500, it's probably because network architecture is chosen in such a way that it would take long for you to reach it. You might pick one of two solutions. You can either reduce the step size, as in like 10 to -4, which will decrease initial performance, initial conversions, but make algorithm much more stable. Or you could do something else, like build a better, bigger network, or if you have any questions, raise your hand at any time. We're gonna. OK, so just to see what happens. So at this point, it almost randomly reached 500. And we're going to see what our agent learned. And then I'm going to show you the code again. In Gym, there's a nice interface called Monitor, which allows you to record some sessions. And we can see that our agent more or less learned to balance. Good for him. And then you can even view the video in a notebook, probably, depending on your browser. If you're on macOS, then too bad. OK, so the cool thing about OpenAI Gym is that it has a lot of environments, like maybe Mountain Car or Acrobot or others. Some of them are simple environments, like, for instance, yet another mechanical thing with a robot. And others, so in this case, it's a robot that tries to reach this point, but he can only control this joint. And other environments are more like entire games. It should be. Yeah, so you can reach Atari games here as well. The only problem with Atari games is that our two-layer dense neural network will probably not be able to beat this guy because it's just it requires better capacity. We're gonna switch to them later on, I hope. And so first, if you got this one working, then you have two options. The rational option is to see if there is anything left from lunch, or do some phone calls or whatever you have to do. And the irrational option is to switch to the second part of our seminar, where we actually train a neural network to actually perform kung fu on this neat Kung Fu Master Atari game. So we are actually legitimately teaching neural network to beat humans with to harm humans with his awesome kung fu skills and get away with it because it's awesome. And this is done with almost the same algorithm, but it uses a baseline from yet another neural network that predicts the average reward. And this kind of joint algorithm is called actor critic. But for now on, let's leave this as an optional assignment, because a lot of you requested that I show what happens in the main kind of training code so that you can fix any errors if you have them. Just let me this time build a slightly bigger network. OK, it's MacBook. I can afford building bigger networks here than on my teeny laptop, teeny tiny. Yes, and this particular game has a different observation size. I've changed the game to Acrobot, to this one. Its observation size is 6. So the only thing we have to change is we have to design a network which has 6 inputs here, or actually state dim observations. It's not required if you're not switching to Acrobot. It's just me trying to do stupid stuff. And again, we have 3 actions here. So hard coding 0, 1 was a bad idea. However, OK, here we have negative rewards for most of the stuff, but the formulas don't change. And let's leave our agent to do something. It's probably never going to reach 500, because in this particular game, rewards are distributed differently, and they are always negative. Yes, the rewards are always negative, so there is no point in this code. But the way we train it is all the same. We compute cumulative rewards at the top. Then we use them to maximize cumulative rewards, and we also regularize with entropy. So here's the code. We created optimizer here at the top, giving it agent's parameters. And then we just say, optimizer, would you kindly optimize for us? Atari Util скачайте из репозитория, интернет должен был появиться. Нет, это файл. Yeah, for the second part, there is a special thing called Atari Util and another thing called envpool, which are files. Those files are already in the repository, so you just have to git pull them to get the files. But it's gonna require you to connect to the internet, and we've probably fixed this by this point of time. Смотри, второй он бонусный. Вечером еще никто не будет. Да. Если он у меня скачан. Если он скачан, то он просто импортируется через импорт. Просто выполняешь работу. People install Gematria. Yeah, again, so, sorry, for the second part, if you're currently busy doing it, you have to do the following. You have to pip install gem Atari. So we can see our agent does some stuff here. And while it does so, have to pip install gem Atari. So here it goes. It's going to install a plugin for Gem, which allows you to make Atari games. But in case of this laptop, it's already been installed. And in general, what happens here isn't changing that much, except our neural network is a convolutional architecture. So we have several convolutional layers, followed by this neat thing, recurrent neural network, LSTM to be exact, which does the following. It goes over a sequence of states of your observations to actually try to make actions based on not just current observation, but maybe an agent's memory from previous observations. And then predicts the logits and the state value. This is basically, okay, did Sergey Bortnov cover Advantage Actor Critic? Okay. Advantage Actor Critic. What? A2C. Алгоритм. Короче, видимо, не покрывал. Okay, so then let's do the following. Since it's already 15:45, let's wrap up. So the first, raise your hand if you have any difficulties or for some reason you haven't finished doing the reinforced PyTorch, not to a state where it trains. If you have any difficulties, товарищи семинаристы, они в вашем распоряжении. Okay, so this was the main kind of part for the seminar, and in the next seminar, Arseniy Ashucha and others are gonna teach you to solve the same environment, but this time with kind of more awareness of what agent is doing, because you're gonna use distributional reinforcement learning. So if you are interested in policy gradient, if you want to read further, there is a file called readme.md here, which points you to a number of materials from both basically DeepMind affiliated lectures, YSDA affiliated stuff, and OpenAI affiliated lectures, and a few articles about why this thing converges, how it converges, and so on. Yeah, so if so far your belief in policy gradient was purely religious, you can swap from religious belief to actually understanding by reading. Yeah, this one. And it's probably going to look much better if only I had access to the internet. I know what I'm going to do. Yeah. It's going to be available there in the repository if only you could download it. Sorry, guys. And I think we're going to wrap up. If you have any questions, we're going to be there for you. If you have any technical issues, we're going to fix them before the formal end of the seminar. Otherwise, you are free to explore other chambers in this facility or do something else.